about to do two problems. The first one is where the two hydrogen atoms collide head on head, and the collision brings about the atoms to a halt. Immediately after the collision, both atoms emit a 121.6 nanometers photon. So we're trying to find what the speed of each atom was just before the collision. As we know, this is an inelastic collision, so each atom loses its energy by emitting a photon after collision. This energy of the photon is equal to the change in kinetic energy of the atom, and this is given by the expression right here, which equals half mu squared minus half mv squared, where m is the mass of the hydrogen atom, u is the initial speed, and v is the final speed. As we know, it got into halt right after the collision, so both the speed of v equals 0. So E equals half mu squared minus half m0 squared. So energy of the photon is actually equal to half mu squared. The expression for energy of a photon equals hc by lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of that photon. We know the Planck's constant value is 6.625 into 10 to the power negative 34 joules per second. C, speed of light, 3 into 10 to the power 8. M, the mass of the hydrogen atom, which is 1.67 into 10 to the power negative 27 kilograms. And lambda, which is 121.6 into 10 to the power negative 9 meters. Putting this all values into the equation that we got earlier, we get the value of u. That's the initial speed, which is 4.42 into 10 to the power 4 meters per second. So the initial speed of each atom just before the collision is 4.42 into 10 to the power of 4 meters per second. Now, the second problem that I'm about to do is a beam of electron that is incident upon a hydrogen gas of electron. Now, we're trying to find what is the minimum speed that most the electrons have to pass for the emission of a 656 nanometers light from the 3 to 2 transition of hydrogen. As we know, initially atoms are in the ground state. The electron can only give energy to the hydrogen atoms when they are in the ground state. So the speed of the electron must be enough to raise the hydrogen atom from the energy level 1 to level 3. We know energy of the nth level in a hydrogen atom equals negative 13.6 electron volt over n squared, where n is the state. Is telling you what state it is in. For example, for ground state is level 1, so is E1. So we have 1 as the number. For level 3, we have a 3 there, 3 squared, we get 1.511 electron volt. So then we get the energy difference between these two levels, which is final minus the initial, E3 minus E1, which is 12.1 electron volt. So the kinetic energy from 1 to 3 is 12.1 electron volt. We also know the formula for kinetic energy, which is half mv squared. So we can equal this half mv squared to 12.1 electron volt. So V equals 2 times 12.1 electron volts times, we're now then converting this electron volts to joules, multiplying it by 1.6 into 10 to the power negative 19, which is the charge of an electron. And then we get it into joules, divided by the mass of the electron, we get the speed, which is 2.06 into 10 to the power 6 meters per second. Now, the next question is, what is the potential difference to which the electron must be accelerated to have that speed? So we do the same thing. E times V gives you the potential energy that it must the electron must pass through. Then we equal to kinetic, which is half mv squared. We plug the value of V that we got earlier, which was 2.06 into 10 to the power 6 meters per second. M is the mass of the electron times 2e, which E is the charge of an electron, 1.6 into 10 to the power negative 19, and we get 12.09 ohms, which is close to the potential that we got earlier too. That's all for today. Thank you very much.